Hey, more on finding local extrema. So let's just jump right into it because we're just doing some more example problems. So we're going to do two problems here and maybe give you a quiz problem. I don't know. We're going to find the intervals on which f is increasing and decreasing. And we're also going to find any local mins or maximum values of f. So here's the game. You want to find your critical values. We want to set the derivative equal to 0 and solve. But we also need to pay attention to whether the derivative, where does it not exist? And this is a good example of where the derivative won't exist somewhere. So let's just run right through it. I don't want to do a product here, so why don't we just do a little bit of algebra, bring it in, and we get x to the 4/3 minus 4x to the 1/3. Now let's take a derivative. We take a derivative on this bad boy, and we're going to get what? 4/3 x to the 1/3 minus 4/3 x to the, what's that, negative 2/3. Okay, now we want to check two things. We want to check whether the derivative doesn't exist, and we want to check whether the derivative equals 0. So we start right off the bat, and we can do this quickly by just saying, wait, let's change our negative exponents. Oh, there we go. Cool. Look right down here. There's an x in that denominator. What can x not be? Huh? Huh? Let's go. Let's go. We found a critical value. X equals 0 is bad. That's a critical value. Because it shows where the derivative does not exist. Because, what? F prime. You can't divide by 0. Cool. And then our next game is going to be set this thing equal to 0 and solve. Sweet. So why don't we just multiply everything by, I don't know, let's multiply by the reciprocal of something. Let's just multiply by 3x to the 2/3 power over 4. You're at the reciprocal of this bad boy. So we bring that in and we get, that's 0, and then we bring that in, and we're going to cancel out our 3's and our 4's, and x to the 2, that's just x. I'll let you figure that out. The 4's, that's exactly what we wrote in there. That's just 1, and then, oh shit, x equals 1. We found x equals 0 and x equals 1 as our two critical values. There's other ways of solving this, but we found out where the derivative does not exist, where the derivative does not exist, and then we found out where the derivative equals 0. But they're two important things, because now we're going to use these values to do our interval testing. All right, we found a value at 0 and 1 from up above. And we have our derivative. So let's write our derivative right above. F prime of x is equal to, and I write it in the more friendly way. Cool. So now we want to take values and plug them into our derivatives. Right here. Prime of, f prime of. And we want to find these values in between. In between. We want to find out whether they're positive or negative. So we want to choose a value that is smaller than 0. And let's go with -1. We want to find a value that's in between 0 and 1. Let's go with 1/2. We want to choose a value that's larger than 1. Let's go with 2. All right, now, oh shit, it's negative. And now we go to our next one. Plugging in 1/2, oh, that pops out, and oh shoot, that one's negative as well. Huh, so it's decreasing. Something happens at 0, some issue, and then we're decreasing again. Now we go over, we plug in 2, right? We're going to 2, we're plugging that into the derivative, and oh, there it is, it's positive. We found out. Oh shit. So we found our critical values, not what the question is asking for, but we find our critical values, and then we do a little interval testing, because now this little interval has told us everything we need to know. Let's start by answering the question, the first one. Where are we increasing? Well, we're increasing from, well, that's decreasing, and that's decreasing. So nowhere there. We're increasing from 1 up to infinity, right? Because we got our 1 right here, up to infinity. So there it is. We got our 1 up to infinity. And then we're decreasing. Well, it looks like we have a couple intervals where we're decreasing. Well, we have from negative infinity up to 0, right here. Up to 0. And then we need to use a little union, because it's not decreasing actually at 0. Maybe it is, kind of technically, but we're not going to say that, okay? We're just not going to say that. There's some sort of issue. We're going to say 0 up to 1. It actually depends upon who you ask as to how you state this, but we're just not going to talk about it. Just going to write it in this way. And if you wrote negative infinity up to 1, I'd be okay with it. I just need to see that you had that 0, that issue in there. This is not always the case, that just because the derivative does not exist, that it's just going to run right through like this. So we found it, but now let's talk about, do we have any local maxes? And a local max will occur where you have something, what, increasing, then decreasing. So what's that? Positive, then negative. So do we have any going from positive to negatives? Nope, we don't. So there's none. So we have, what about local mins? Well, local mins, that's when you have it going from negative to positive, right? And we do have one, and that happens right there at 1. Right there, we went from negative to positive. So let's pop in that 1, and we can say that at f of positive 1, we have our local min. Notice, just because we found a critical value, we had a negative and negative. This can happen, decreasing then decreasing. Give you another example of something like that. Maybe the negative cubic. You're going to have a derivative equaling 0 right there in the center, but it goes decreasing then decreasing the entire way through, but just for a moment it's not decreasing. Okay, done with that. So here's actually what was happening with the shape of your graph. Here it is all graphed out, and you could see that from we actually are decreasing the entire way through. Look, decrease, whee, all the way down to 1. So we could technically, if you said negative infinity to 1, you would 100% be correct. And then the rest of it saying that we just take off, and we're increasing the rest of the way. We only had our local min right here at 1, and there it is. Next problem. And this one we're going to go, oh shit, I showed it to you. You can't see it yet. And here we go. This one's, there's not as much algebra to it. It's pretty straightforward. Just wanted you to see something, a little issue. So let's go through it. Let's take a derivative. You could bring the e to the x in, but you're still going to end up having to do a product either way. So let's take a derivative on x squared minus 3, and let's leave e to the x alone. So that's going to be 2x times e to the x. Plus this time, let's leave x squared minus 3 alone. Let's take a derivative on e to the x. Neat. Well, we don't have to worry about, because we're going to find critical values now, right? We're going to take a derivative, set it equal to 0, and solve. We're also going to check and see where the derivative doesn't exist. The issue, or the thing is we have now, no issue, no problem actually. E to the x has no domain issues, and polynomials, x squared, 3, and 2x, they have no domain issues either. So we can just set this thing equal to 0 and solve. Well, let's yank that e to the x out. That was one of the reasons why we wanted to factor these before, is because once we take the e to the x out, maybe we can clean this up and solve a little nicer. So what's left is that 2x, the x squared, and the minus 3. So I'm going to write it in descending order. The x squared plus the 2x minus 3. All right, now we have that thing set up. Now we can say it's e to the x. Let's factor it on up. What's that? X plus 3 and x minus 1. Set equal to 0. Well, let's go. We have 3 factors, huh? E to the x, x plus 3, and x minus 1. Let's set those bad boys equal to 0. So we go e to the x equals 0, but you know what? Good news, that can never equal 0. So we can just ignore it. All right, that's that exponential function that you already know how to graph. We got x plus 3 equals 0, hence x equals negative 3, and x minus 1 equals 0, hence x equals 1. Well, there we have it. We have our 2 critical values. Only 2 popped out of there, even though we had 3 factors, because e to the x can never equal 0, not the exponential function. Dope. Now let's run through, and we look, and we're like, well, we got an interval test again. We got to look between negative 3 and 1, so we're going to want to check with our derivative, f prime of, f prime of, f prime of, and what value is smaller than negative 3? What's small? Let's say negative 4. What's a value between negative 3 and 1? Let's go with 0, and the value larger than 1, that's 2. So now we run through, we want to take a look and see what's happening with our derivatives. We punch it back into our derivative. That would be punch it right back into this, or this, or this, whichever one you want to use, which will make it easiest. It'll probably be easiest on this last one, because all you're caring about is the sign. So once we punch it in, we're like, oh shit, that one's positive. Once we go here, we got, oh, it's decreasing now. And now we're back to increasing just by plugging those values in. So to answer our question, we could say that we are increasing, And that's going to be from negative infinity on up to negative 3. And then we union that with, well, from 1 up to positive infinity. And we are decreasing only in between negative 3 and 1. Now we use the idea of a local max. A local max will occur where it goes from positive to negative. So that's going to be at f of negative 3. And we're going to have our local min hanging out at f of 1, because that's where you go from that negative to that positive, right? And there we have our solutions for these fun-filled problems. Now here's the graph of it right down here. Everything matches up where we have our increasing. It's flat, kind of going towards a asymptote, and then we drop down to negatives, or a decreasing function, then increasing again, where the e to the x never made that thing equal 0. Now here is your quick little quiz problem. Now here is your game, what you need to have done. Please, we're going to take, now this is, now this is all algebra. This is all algebra. H of x is equal to 4/5 x to the 5th plus 3x to the 4th minus 7x cubed minus 15 over 2x squared. Oh, it just keeps going. Algebra. You remember your rational root theorem, don't you? So here it is. We have h of x is equal to 4/5 x to the 5th plus 3x to the 4th minus 7x cubed minus 15 over 2x squared plus 20x plus 1. And we're going to want to know the same instructions as to what we had before. You have the same instructions as our examples. Increase, decrease. And then local max and mins. Now here's the big thing. Exact values of x only. I'm looking at work, not answers. Work, not answers. So if you just look at the graph and you just try and write down some decimal approximation, I will give you a total of 0 points. If I see that you're using just some like factoring with no steps, you just can magically factor like a beast, I will give you no points. I want to see your steps. It's called the rational root theorem. Look that shit up if you need to. But you're going to want to take a derivative, set this thing equal to 0 and solve. It is a giant pain in the ass because you're going to need to use what's called the rational root theorem. So have fun with that, but I need you all to be ready to handle something of this manner. So this will be your next quiz. I'm not sure what the number is, but it'll be popped up there soon. See ya.